for the supply node, x12 plus x14 less than or equal to 200. So this was the original constraint that we wrote, and we're trying to change it to the format in this inflows subtract outflows greater than or equal to demand or supply. Okay, and we know the supply is 200, and we can using a negative value, which is negative 200, to represent the supply. Okay, so here these two are outflows, right? Okay, so if I want to change to be this format, it should be subtract okay, because now there is no inflows, inflows 0. Okay, isn't that the same as this one? If we multiply a negative sign on both sides, so it will be this, and the sign will change direction, which is exactly the same, right? So with this, we can put all of our constraints, whether it's a supply node or a demand node or the transshipment node. We can put the constraints all in the same format. Inflow minus outflows greater than or equal to the demand or supply. Okay, and we can do this is because we can do the greater than or equal to sign is because our total supply is greater than the total demand. Okay, so what we're saying that for all the demand nodes and the transshipment nodes, the volume that stays at that node should be greater than or equal to the demand there. Okay, and then for the supply nodes, we don't supply more than we don't supply more than what we have at that supply node. Okay, because we know there is already excess supply. Now, what if in this problem, what if here I change this to be 100? So now we only have 300 numbers of supplies, and we know that the demand is 380. That means we are not able to fulfill the demand. How should the constraints to be changed? Okay, think about this. If we don't have enough supply to meet all the demands here, can we still use this constraint? Or should we change the sign here? Okay, so let me tell you like this. Okay, if now if the sign is changed to be less than equal to, then our constraints will be inflows minus outflows need to be less than equal to the demand or supply. Okay, now with this, let's think about if it makes sense. Okay, if we look at the supply node, if we look at just the supply node, now we know that we don't have enough supply to meet all the demand. And with this inflow minus outflow less than equal to supply, if we just look at here, and we know that in this format we use a negative value to represent the supply. Okay, so once we change this relationship here, this side need to be less than equal to. Okay, and here will be greater than equal to. So for this first supply node, node 1, we have this constraint. What we are saying is that since we don't have enough supply to meet all the demand, let's make sure to supply to send out all we have. Okay, so that's similar to what we talked about in chapter 3, right? When we change the supply and demand relationship, we change the sign of the supply nodes. We're saying, okay, if we don't have enough, let's just send out what we have. So here it could be equal to, but to be consistent with other constraint, we set it to be greater than equal to, but we know that no more than 200 will be sent out. Okay, so it will be greater than equal to, let's send out what we have. Okay, and then if we look at the transshipment node or the demand node, so for all of those nodes, now the signs will all be, oh, sorry, not those ones. Yeah, we already changed them. Okay, so would be here would be greater than equal to, greater than equal to. And all the transshipment node and demand node will have less than equal to. So all of these signs will be changed to be less than equal to, less than equal to. And if you think about it, for all the supply and demand node, for all the transshipment node and demand nodes, what we are saying is that since we don't have enough supplies to meet everyone's needs, let's just don't supply anyone with more than what they want. Okay, so Boston only required 100 units. So let's just supply less than equal to 100 units. We don't supply more than that. Okay, it could be less than that because of the total supply-demand relationship. But we make sure we don't supply more than what we have. Okay, and since we are shipping out all we have from those two supply nodes, so we make sure that and also based on those costs, transportation costs, we're going to find the most cost-effective way to meet the demand as much as possible. Okay, and same for the demand node. Okay, we're just saying for all the transshipment and demand node, we're just saying we don't supply more than what is needed. Okay, so hope with this explanation it makes sense to you. Okay, then let's do a summary. So for this problem, what we did first is define the decision variables using the general way. Okay, and this becomes the standard way of defining decision variables in all network problems. And we know that number of arcs determines the number of variables. Okay, and objective function is pretty easy. Minimize the total shipping cost, and just make sure you don't miss any of the routes. Then in this problem, first we determine the total supply and demand node, and we find out that total supply is able to meet the demand. Okay, oh, did I make a mistake? I calculated as 380 supply, but anyway, so the relationship is the same. Okay, and for each node, we need the constraints look like this. So inflow minus outflow greater than or equal to the supply or demand. That's because of this relationship here. Okay, so for the constraints, the node 1, which is the supply node, we first wrote in this format because that's the most familiar way to us. but later we talk about we can write in this format because they are exactly the same. And this is the way that conforms to this standard constraint format. And for all the other constraints, we put them all in the same format. It's the inflows. So, for example, by looking at this constraint, you can tell that's a supply node because it has a negative value here, and this is negative value here, supply node. Okay, and so inflows minus outflow inflows. So this one, by looking at the constraint, you can tell that's node 4, which is a demand node. It does not have outflows. Okay, so all the constraints take the same format. Inflows minus outflows greater than equal to the supply, the supply represented by a negative value or the demand. Okay, and last we need to add a non-negativity constraint for all the decision variables. Okay, and the constraint standard format is called constraints that following the balance of flow rule. Okay, and this balance of flow rule is for us to determine the sign that we should use in the constraints. Okay, so we look at the for any minimum cost network problem. Okay, we look at the total supply and total demand relationship, and then apply this balance flow rule at each node for the constraint. Okay, and you can see that the sign here determines the sign here. Here you can just put greater than equal to or greater. That should be the same. Okay, and one thing I want to emphasize here that why we need to use this balance of flow rule constraints, which means this format. Okay, one advantage, of course, is to put all the constraints in the same format, which is not really why we want to do it. The main reason that we want to use this balance of flow rule is because when a network problem only has constraints that conform to this balance of flow rule, and plus some simple upper or lower bound. Constraints. Then, if the problem has integer coefficients, we will be guaranteed to get integer solutions. Okay. For example, in this case, all of our constraints conform to the balance of flow rule. Okay, and their coefficients are integers. Okay, like the right hand side, these are all integers. And we only have a simple lower bound constraints besides those balance of flow rule, which means is x greater than equal to 0 or any numerical value, or less than equal to a numerical value. So with this, it's guaranteed that we will find integer solution. We're going to implement this later, but I'll show you the solution here. Okay, you can see in the solution, all the decision variables come out to be integers. Okay, so that's the advantage of having the balance of flow rule constraints. Okay, so that's this problem, and we're going to formulate this problem in Excel next week.